Okay, so my name is Tony Keaveny. I'm a professor of mechanical engineering and bioengineering here at UC Berkeley. And I direct the Berkeley Orthopaedic Biomechanics Lab. So what I'm presenting today is a new project we're doing with ParLab, which is writing off some of the successes we've had in the field of orthopedics, but trying to exploit advanced computation even more and address some important clinical problems. So I'm not going to talk much about computer science. This is what you can do if you've got interesting applications and a need for computation, advanced computation. So the vision here is that we would like to take the information that's in medical images, and by incorporating physiological modeling and advanced computation, extract more information out of those medical images than is currently being done in clinical practice. If you have a CT scan or an MRI scan, for example, the radiologist generally just looks at the scan, and based on their experience, they make a qualitative judgment as to what's going on. And that's entirely appropriate for many medical diagnoses, but there's a whole range of important medical problems where you need quantitative information that you simply can't get from looking at the scan or making even simple measurements. So my expertise is in the field of biomechanics. I take mechanical engineering and apply it to living systems. So I look at the world through my biomechanics lens and medical problems through my perspective of which medical problems have an important biomechanical component. And what I'd like to do then is to merge the advanced computation with the information in these 3D medical images with my particular expertise in biomechanics, and from that try and improve healthcare. So very focused on helping people directly. This is not an academic endeavor. The way you can translate this into actual useful products is through improved diagnostics or surgical planning. And eventually what you're trying to do is produce information that improves the management of patients that come in. So the biomechanics and the computation allow you to transform the medical image into outcomes that have clinical function. So I started this work in the orthopedics area, and this is a finite element model, or it was a finite element model. I love PowerPoint. It's got a mind of its own. It was an image of a small piece of bone under a microscope that we can do virtual compression to understand the strength properties of that bone tissue. Now, if you noticed on that image, and let's see if I can go back. Yes, there's all these small little elements here. This is a finite element numerical model. So think of each little box as a sampling point where you can do a mechanical analysis. So in these models, there was 5 million degrees of freedom. The real bone specimen here is about 4 millimeters apart. And we did this work with some folks in computer science, Jim Demel and Mark Adams, and it was very state-of-the-art a few years ago. And then we extended it further to looking at larger pieces of bone. And here is another finite element model of a slice through a human vertebral body. And the red colors show the regions of high stress as you compress this vertebra. So these computer models had 500 million degrees of freedom, and we won this Gordon Bell Prize in 2004 for the scalability of the parallel code used to analyze those problems. Now, you can't do this clinically. The images required here are too high resolution. You can't get them clinically. But we wanted to take what we learned from this and turn it into some kind of clinically useful application. So we developed means to make these computer models on clinical resolution images. Finite element models of a person's spine, you compress it, you can predict how strong the bone is and see if that can be used for applications such as osteoporosis. So in 2003, this work appeared in a research journal. In 2008, this is a clinical journal. So we successfully translated this across. We spun out a company. And here are some results from a clinical study on real people. The blue dots here are people who have fractured their hip. So we CT scanned a whole bunch of folks, about 3,000 people, followed them for 7 years, and tried to predict who was going to break their hip and who wasn't. So the blue points are people who broke their hip. Black points are a control group that didn't. This is the clinical standard that's used for assessment of osteoporosis, and this is the cut point that's used to decide whether you go on drug treatment or not. So if you're below here, you would be put on a drug treatment. And here's our measure coming out of these computer models. And what's important here is we identified all the folks that are currently identified, but we identified as many other people who would just not be touched clinically. So we've got double the sensitivity as what's used clinically from this new technique. So we're trying to get FDA approval for this. And this is a nice example of taking some computation, very high performance computation, coarsening the resolution to something that's realistic, and then actually introducing it into clinical practice. So we wanted to do the same thing for a more immediate problem. Breaking your hip is very serious if it happens to you, but your bones don't hurt if you've got osteoporosis, and everybody's in denial that they're ever going to die or get sick. So you tell somebody they're at high risk for osteoporosis, and they're in denial. I'm not. How could I be? I feel fine. So it's a challenge to implement it clinically. So we wanted to get a more immediate application that there would be absolutely no question about the need for it clinically, and we came across this application for stroke. So stroke is the number 3 killer in the United States. There are almost 1 million strokes a year. 25% of them happen in people who've already had a stroke. There'll be quite a few strokes have occurred to people by the time I'm done with my talk here. Mostly an elderly disease, but not entirely. But the issue is if you come to the hospital with a suspected stroke, because you can never tell by looking at somebody if they've had a stroke, they'll take some CT scans, maybe some MR scans of your brain to try and see are the characteristics there typical of a stroke. But if you have come to the hospital 3 to 4 hours after having your stroke, even if they diagnose that you actually have had a stroke, they will not treat you. You will be managed in intensive care, but they will not give you any treatments. And the reason is, when you have a stroke, it's a blockage of a blood vessel. That's the most common type of stroke. What that means is downstream of the vasculature at some point, some tissue will not get adequate blood flow, and that tissue will begin to die. So that's the disability you suffer from having a stroke. You can be lucky, and this can occur in a part of the brain that doesn't affect much of your function. You can be very unlucky, and even a small amount of tissue damage could result in loss of speech or turn you into a paraplegic. So this is the immediate consequence, but the reason they won't treat you is because the risk of bleeding occurring downstream is too high. So the stroke itself is a blockage, but remember the blood has been pumped up into your brain, so it gets rerouted, and if the pressure builds up too high, then you'll actually burst the blood vessel someplace else and die. You will die from that. So they've just figured out empirically that if they wait to treat you 3 to 4 hours afterwards with a blood thinner, which is the most common treatment, the risk of hemorrhage is too high, and they simply don't do it. So most people fall into this category of 3 to 4 hour windows, because most strokes happen while you're asleep or you're at home. You don't even know you've had a stroke until a few hours afterwards in some cases. So we want to see if we can take the images that they use to diagnose you and provide the physicians with information that will allow them to treat people beyond that window. So extend the window of treatment and then reduce the number of deaths and reduce the amount of disability that results in stroke. So one of the interesting things about your vasculature is that this is the classic, this inner circle here is your main vasculature in the brain. That's where most of the strokes occur. It's called a circle of Willis. About half the population have a textbook circle of Willis like this. About half the population have some permutation of that. So if you add the permutation of the geometry of the circle of Willis with the location of the stroke that can vary, you put those two together, then of course you have what we call substantial heterogeneity. And what we're proposing is that in some cases somebody will have a stroke in such a part that when the blood is rerouted around, it'll be at very high pressure and put you at high risk. So for example, the stroke can be in different parts of the vasculature, and then in some patients you're just literally missing some of these branch points. So this is the heterogeneity that we can pick up in the CT scans. So our solution is you start with the CT scan that the patient is already given to diagnose the stroke. So we're not talking about any new type of imaging technology. This is using pre-existing data that's taken as soon as the patient comes into the hospital. we're going to do a blood flow analysis based on a model we create from the patient CT scan. We're going to simulate the treatment, which is the most common one is giving a blood thinner, and we're going to assess the stresses and the flow in the main artery here, the circle of Willis, and then in the main vessels. And then based on those results, we're going to try and risk stratify the patient and either put them into a low risk category or a high risk category or in between. If they're at low risk, if there hasn't been much of a change in the blood flow characteristics as a result of the stroke, there's just a blockage and no real downstream complications, then we would conclude it's safe to treat the patient. On the other hand, if it's so bad, if the pressures are so high downstream, then why not treat the patient? They're probably going to get a hemorrhage and die. So we think we'll be able to stratify into these two groups, and then there'll be probably a half or two-thirds of the patients we won't touch after that. They just leave them. So the improvement will come from changing the course of treatment to these two groups of patients. So this is what we're trying to do. Technologically, we've got 60 seconds to get our recommendation, our risk stratification, to the radiologist upon receiving the CT scan. They're literally waiting on as soon as the CT scan is taken, the radiologist is looking at it, deciding what to do. So we've got 60 seconds to do all this image processing, blood flow analysis, and print out a report. So the strategy then is we started the CT scan, we have to do some image processing. That's going to lead into a simplified blood flow analysis. If you remember from the bone work, to make these things work clinically, we had to coarsen down the resolution. We're taking the same liberty here because if you were to do a full big 3D flow analysis, you'd never get it done in 60 seconds. So this is the compromise we're making, and of course we're hoping that we'll still get useful information out of the analysis. We'll validate these simulations with a fully three-dimensional analysis, which we're doing by coupling pre-existing parallel codes. But we will do an observational clinical study where we'll take 100 or so patients, do our analysis on them, but not touch them, make our predictions of what should happen, and then correlate it with the clinical outcomes. And what we're betting on is that when we say the risk is high, those patients have a very high risk of a hemorrhage. When we say the risk is low, those patients have no problem at all. But that observational study would be based mostly on predicting who's having a problem. And then that produces this, then we go on to produce this medical report. The numerical strategy is we're developing all our initial image processing in the blood flow code in MATLAB. We're using BTK and some pre-existing codes for some of the image processing, but eventually we want everything going into this CGITS framework, and I presume you've heard all about that. So we have to deal with, in terms of numerical robustness, and we want to maintain the speed performance. We have to get this done all together in 60 seconds. The actual numerical analysis, we call it 1.5D blood flow. This is a cartoon of that circle of Willis. These are outcomes, which is the blood flow at the various exit points. We are going to capture the 3D topology of the patient's vasculature, but we're not going to do an actual 3D blood flow analysis. So we won't be simulating any vortices or complex little turbulent weights or anything within the blood flow. And the cross-sectional properties of the blood vessel we'll probably just assume are circular, but the diameter of the vessel would be based on what we see on the patient's CT scan. And there's other simplifications we're making too. So one thing I want to point out, so we could be successful and actually be able to predict in an observational study who are the people at high risk and have go on to hemorrhage. We're not done. This part is really important. So once we get done with everything I just spoke of, we then have to do a second clinical study, which is an interventional clinical study. And that'll be a randomized study where half the patients will be managed based on our information and half the patients won't be touched at all. It's just standard practice. And at the end of the day, you've got to show that either the number of deaths or the number of complication rates is lower in the group that you used our information to help manage. And if you can't show that at the end of the day the death rate is lower or the complication rate is lower, even though you may be able to predict who's going to have a hemorrhage, if it doesn't ultimately lead to improved clinical outcomes, you'll never get reimbursement and the medical profession won't adopt it. So that would be a follow-up clinical study that would then need to be done. Obviously, you can't make a mistake in this. You can't be predicting somebody is very safe and give them a blood thinner and have them have a hemorrhage on you. You think about that, it becomes very immediate. I'm not going to talk much about the numerical aspects of this because I don't know much about that. I'm very much the user, but I will throw out some jargon here. So we're using a number of the variable motifs. We've got unstructured grids, lots of sparse matrix operations. We've got some machine learning and graphical models coming in on the image processing, trying to separate the vasculature out from the bone, and setting up these meshes at the start is fairly challenging. This is what it looks like the way we set it up numerically. So you take the vasculature and you break it down into just a one-dimensional string, and then you do these computations at just steps along the skeletonized vasculature. So each point here, we can dig into the CT scan and find out what's the diameter of the patient's vasculature and what are the coordinates of each point. But then the numerical analysis itself, it's like laying the blood vessel out in a straight line and doing that. So there's lots of these stencil operations, and we've got small dense systems in terms of putting everything together at the different junctions. So each little branch of a vasculature is self-contained, and it just interacts with the other little branches at these blue sections. In terms of the problem size, we have about 10 to the 4 sampling points along those skeletonized models. We've got about 5 million time steps to take, and these are the number of calculations per point. So we've got 30 seconds to do the blood flow analysis part, and that lays out the performance of this. So it's about a 300-fold performance increase from where we are now, which we think is doable. The image processing is an interesting one. I don't know if any of you guys are interested in image processing. Here's the vasculature here. We have to separate this out from the bone and any other tissues that are not important. We do that, we skeletonize it then, and this is what we do our actual analysis on. So there's some interesting issues here in terms of pattern recognition to be able to separate the vasculature out from tissues you're not interested in. And we actually are doing full 3D analysis too. So on the side, for validation purposes, we're getting into mesh generation for actually developing fully three-dimensional models here. For the image processing, this gives you a sense of the size of the images and the time scales. We're currently, if you do this manually, we're about an hour. It has to be done in 30 seconds. The challenge with the image processing is it can't require user input. So it has to be robust, it has to work every single time, and that influences the way you do it, and it's a real challenge from a computer science perspective. And again, all the image processing is intended to be done eventually in the CGIT framework. So there's a fairly large team here. Panos Papadopoulos is a mechanical engineering professor who's big into finite modeling and numerical analysis. And Jim and Kathy are in computer science here. Armando is our expert in the CGITs part of it. We're collaborating with Lawrence Berkeley Labs on the 3D implementation of this, which we're using, as I said, for validation purposes. One of the folks that was there, Brian, is moving over. He's starting grad school here. These are the students who are currently working on various aspects of the project. And Max is a physician. These three guys are experts in blood flow analysis, and Mark is an expert in the solids and three-dimensional parallelization of the solids code. So if anybody has any questions, I'd be happy to try and answer them. Thanks.